discussed about what are algorithm, and then we have seen many concepts which will be coming under the algorithm. And then we have seen while discussing algorithm analysis or complexity analysis. So for that, we are using something called as asymptotic analysis. So that was the topic which we have discussed in the previous class. So while discussing asymptotic analysis, we have seen what is it exactly, and then how we calculate the time complexity. Okay, how actually we are calculating the time complexity, what is exactly the time complexity. Then we have seen determining the function of n. Okay, nothing but while finding the complexity, we were doing the finding the function, that is nothing but f of n for the input. What we were finding there is the growth rate of that particular function whenever different amount of input is given, how it is going to give the things. Okay. So then we have seen, while we have taken one example by taking like f of n is equal to 5n square plus 2n plus 12. And we have seen the drastic change, how the time, or to say the percentage of the time consumed for running that particular algorithm with that equation for each term of that function, how the time was being divided. Okay, and the drastic changes we have seen when the number of input was actually increasing. So depending upon the number of inputs and the number of operations taking place on them, we are going to predict, or we are going to say about a time complexity. Okay. So looking, after solving that particular equation with the by applying the number of inputs we are having, like we have seen, when I have 10 inputs, what is going to be the value, when I have 100, when I have 1000. Okay, so what happened was, when there is a constant term, the negligible amount of time is taken by that particular term, but which have actually taken the most of the time when we compare all those function term is nothing but the quadratic one. Okay, which is square terms have taken much of the time. Okay, and at that time we have come through like depending upon the time, okay, which bound, like higher bound or lower bound or average bound, we are having in complexity analysis, we have having three cases, which we call it as worst case, best case, and average case. Okay, and I have also told you, depending upon the case we are going to identify, or depending upon the different scenarios what we are going to identify, or using which scenario we are actually going to write the complexity of a particular algorithm, we have three different kind of notations. Okay, so each of which is associated with the cases. So we have worst case, we have best case, and we have average case. So this worst case we'll be using big O notation, and for best case we will be using omega notation, and for average case we will be using theta notation. So in today's class, what we are going to say is, we'll take one example and see what exactly we are going to depict by using big O notation. Okay, why I'm using the notation is, for example, if I want to say that the distance from here to there is this much distance. Okay, I can give it in terms of numbers, but the measuring parameters, there are different measuring parameters like meters, centimeters, kilometers. So we are notating it so that we are setting the bound for it. So now if I consider centimeter, meter, and kilometer, which is having higher bound, kilometer, because we know what exactly it is, giving us, like 1 kilometer is equal to 1000 meter, correct? So in the same way, depending upon which case scenario we are going to depict as a time complexity, we will be having different notation. So always we will be using big O notation because it is this of worst case. Now, why are we considering worst case? When we have worst case, when we have best case, and when we have average case. Why are we taking worst case is because usually when I have an algorithm, okay, or anything if I have, general, we'll take a general example, okay. So someone um, is inside the room, okay. For example, I'll take the example of we'll be going for shopping, okay. I want to trial a dress and we'll be waiting in the trial room. So we'll wait like when the person will come out so that we can go in. So, what possibility will always check? Will always check the possibility for when that person will come or how much of most of the time he will be taking. So that if he is taking time, I can go out, okay, and I can search for few dresses and then get it back so that I can trial there all together. Okay, after that person comes. So if you simply wait, your time is wasted, right? So you won't always consider that okay, what might be the minimum time he will take? Because the time taken for him inside the trial room would be depending upon how much dresses he has taken inside to do the trial, correct? Okay, so here also, when I say the complexity of a particular algorithm, I'll be considering how many inputs I am taking. So whenever the input size increases, what might be the worst, in worst case, what might be the largest amount of time a particular algorithm is taking in order to execute the code. So that is what we have to consider. In real world, we are developing something. Okay, because if client is giving you a problem and you have to find a solution for it. First of all, what they will ask is whether this is feasible, whether this is proper, and whether this is efficiently performing. Okay, whether it is efficient and it is high performance. All those things are asked. So whenever we consider these things, what matters is how much amount of time will your algorithm take in order to complete software or this complete solution, whatever we have prepared. Okay, so I have to always consider the worst case. So if I consider the worst case, that is the maximum time taken by an algorithm to finish its execution, what I can do is okay, so I have 2 to 3 developers, and these 2 to 3 developers are very good developers who have developed their own algorithms. Okay, and I'll be selecting them. So, on what basis I'll be selecting them? Depending upon their efficiency and performance, and also less time complexity. Okay, so the time complexity needs to be decreasing. So, for that, I have to consider the worst case scenario. So that if in worst case scenario, if the time taken is more by a particular algorithm, will just reject it there itself. And other things I can consider depending upon the input, the time complexity will increase or decrease. Okay, so that is working like that. Okay, so for the worst case scenario, what might be the most important thing is, as I've told you, for different scenario, we'll be making use of different notation in order to depict the time complexity. So big O notation is nothing but we are using it for worst case scenario. So as I've told you, for the worst case scenario will be the most highly sought scenario in order to completely check for the time complexity. So always we will be considering or always we can see the complexity is written in terms of big O notation. Okay. So now let's see what is exactly big O notation, what is meant by upper bound and all those things we will see. And also we'll take example like how we can actually come into a particular example. Okay, from a function what we write depending upon the algorithm and the code what we implement. From that, how we are getting to know how exactly we can write an algorithm. I mean, how exactly we can analyze the algorithm and give a complexity for it. Okay, by looking at the code itself, I'll be saying like, okay, so this is having this much complexity, so this might not work because I need a very more efficient program or the efficient code which is highly performing. So depending upon that, whatever depending upon the complexity, whatever we having, we will be choosing the algorithm with the lowest complexity. Okay, just give me a minute. Okay, so now let's see big O. Okay, it is told as big O and it is written as the uppercase letter O. Big O notation is an asymptotic notation that measures the performance of an algorithm by simply providing the order of growth of a function. What we are doing, I have a algorithm and I have to check for its performance. I have to measure it. So for measuring the performance of the algorithm, after measuring, I have to provide it with some notation. So that is nothing but we are using the big O notation. Okay. And then we are using the big O notation. And then uh, what are we exactly doing is we are providing the order of growth of the function. Order of the growth is nothing but how the time what the time will be taking depending upon. Okay, so it is directly proportional to, not always it is directly proportional. Okay, sometime for the some terms when I give less input it may take larger time. Okay, so that example we have seen in the previous class. So we are predicting the order of growth of the function depending upon uh, order of the growth of the function depending upon the what to say input. Okay, so big O notation is a way to measure how an algorithm's performance or time taken increases as the input size grows. So as I told you, that is what we are considering as the order of growth of the function. Instead of focusing on exact execution times, it tells us how quickly the time complexity increases in the worst case scenario. Got it? So big O notation is specifically for what? Worst case scenario. And it gives an upper bound. So one more thing is it gives the upper bound on the growth rate of a function. Upper bound on the growth rate of a function means I have a function, okay, and I have to check for the worst case scenario. And this O notation will give us the upper bound. Upper bound means uh, which is the term which is having the higher bound. Okay, means which is likely to be taking the what more amount of time. Okay, so when we do the exercise we may know more into it. So it ensures that the function never goes faster than this bound. Got it? So in this notation what we are trying to identify is we will be showing the upper bound on the growth rate of a function which says that apart from this, above from this, the function will never go faster than this bound. Okay, or yeah, or never go. The time may not go more than this bound. Okay, so that is the upper bound we are setting. So in simple words, it tells us the worst case performance of an algorithm. Okay. Now next we will see. So this is how we show the upper bound. Got it? Now this is my actual function. Okay. And I am getting an upper bound where it says above this bound, my function will never go. So we are getting one upper bound, and this is the most amount of the time which will be taken by this particular algorithm, and we will be showing it. So I'll get to know, okay, so this is the amount of time to the most, okay, utmost time taken by the algorithm which is developed by me. So either in order to improve its performance, always we'll look for the less the algorithm which is having less time complexity. So what we have to do is I have to make some changes to the code in the algorithm, or the logic in the algorithm, so that the time complexity will be reduced. Okay. Now we will take for the example why there the g of n is written, why f of n is written. F of n is my function of that particular algorithm, and g of n is nothing but the upper bound we are setting. One bound we are setting. Okay, above that bound, it will never go. The time complexity will never increase faster above that bound. So if we have two functions, that is f of n and g of n. So what is f of 1? The actual function describes the algorithm's time complexity. And what is g of n? A singular function representing the upper bound. A normal function which is giving the upper bound. That's why we are selecting it. Now, then we say f of n is equal to O of g of n. What we have to say? Big O notation will represent as the upper bound. So this is one function, we are taking it as upper bound, and its value would be what? Our big O notation. So in big O notation, our f of n should be equal to or greater than or equal to the, sorry, f of n should be less than, okay, that bound, whatever we are setting this g of n, no, it should be the higher one, okay. So that needs to be our motor. Means here what I'm saying is, for my f of n, that is for my function, the complexity would be O of g of n. Now I have to see what is g of n, what is f of n, and how I can make it, what, how I can solve. Okay, so my function is what? F of n is equal to big O notation of g of n. Now, if there exists constants c and n naught such that, now here n naught is nothing but uh, your number of inputs. Okay, so c is nothing but a constant. So this we have seen in the last class. We're adding some constant to the equation. So the condition is this one. Okay, we will say that f of n is equal to big O notation of some function. Okay, if there exists a constant and the n naught, where n naught is where there would be uh, n0 would be what, the least amount of input, and here what we are doing is we are considering n as a number of inputs. So f of n is always, it should be less than or equal to c into g of n, which is here, because we are considering the g of n as the highest order. Okay, the upper bound we are considering. So my function, it needs to be less than that upper bound, that is displayed by the big O notation. Now, this means that after a certain value of n, the function of n will never grow faster than g of n, which is multiplied by some constant c. So that is the mathematical representation of big O notation. Now we will see by actually substituting some values to it. Okay, like the values for n. Okay, yeah. the value for the n. Okay, so example, what we'll be having is we're checking if f of n is equal to O of g of n. Okay, because the mathematical notation what we have given for the big O notation is f of n is equal to O of g of n. Now I have to prove it. So what is the condition to prove it? What we need to prove here is my f of n will be less than, or it can be equal to my g of n, but it can be more than g of n. That is the upper bound we have set here. And that is also for the worst case scenario. So we are taking two functions. We know that f of n is there and we have g of n. So one function value will be taking for f of n and one function value for g of n. Now in the g of n, I have only n. That is nothing but a number of inputs. 1 into n I can consider. There is no constant. So we need to check whether f of n is in big O of g of n. Meaning we need to verify. So f of n is in big O of g of n means nothing but my f of n should be less than or equal to my g of n. Now, for this particular equation, actually we have to substitute whatever we have, that is 2n plus 3n, n. So instead of g of n, you'll substitute n. Instead of f of n, you'll substitute 2n plus 3. Now, this is going to be my equation, correct? Now, let's assume the C value. Some constant value we will take, the value of constant as 5 and check if the inequality holds for some values of n. So, now whenever your equation is having equal to some values, we call it as equality. But here the equation is what? Inequality. So, we'll be checking whether this inequality becomes true for some n. So we'll be checking now. We know that we will be considering for different number of inputs, or okay, the size of, depending upon the size of the input, we will be see what might be the complexity. So for big O notation, we have to check whether your f of n is always less than or equal to your g of n, but with some constant multiplied to it. So we are taking now for if the value of n is 1, which is substituted for the n which is present in this equation. So 2 into 1 plus 3 less than or equal to 5 into 1, correct? 5 is nothing but we have assumed the C value as 5, and then the value of n is 1. So 2 into 1 is 2, 2 plus 3 is 5. So in my left hand side, I have 5. And in my right hand side, I have 5. So the inequality now it is what? 5 less than or equal to 5. So now both are same, right? So the equality function there, it is turning it to be true. That is why for the n equal to 1, when the number of inputs is 1, the inequality holds. So for that case, we have f of n is equal to g of n. Now next thing what we have is n equal to 2. Now we will check if the value of n increases and if the number of input becomes 2, then what will happen to that particular equation or inequality, whatever we are having. So 2 into, now what is the value of n? 2 into 2 plus 3, which is less than or equal to 5 into 2, we have to see. Yes, obviously it is. So 7 is less than or equal to 10 means what? That particular thing will always be less than our n function. Okay, so that is, again, that is depending upon what constant value you take. Okay, if I take some lesser constant value, it wouldn't have been the case. Okay, so so this is true. Yeah, so this is just an explanation of that particular thing, whatever is there. Hence, that are true, we will be considering it as f of n is equal to O of g of n, because we could create an upper bound for a code. So we know that for any value of n, it will satisfy the above condition, that is 2n plus 3 is less than or equal to c into n. Any example if I take and with the value of 5. So if the value of c is equal to 5, then it will satisfy the condition 2n plus 3 less than or equal to c into n. So we can take any value of n starting from 1, it will always satisfy. Okay, so you try that by tracing and by giving it the value other than 5. Now, therefore, we can say that for some constants t and for some constants n naught, it will always satisfy 2n plus 3 is less than or equal to c into n. As it is satisfying the above condition, so f of n is big O of g of n, or we can say that f of n goes linearly. Okay, so when f of n is there, then we get the g of n also, which is nothing but we consider it as linear growth. Okay, what we are actually trying to write in the big O notation is what is the growth of the algorithm. Okay, growth rate of the algorithm. So now how the what type of growth it is having? Linear growth it is having. Which one? Big O notation. So therefore it concludes that c into g of n is the upper bound of the f of n. Means I have a function upper bound. The last bound is g of n. Above that, it may never go higher. Okay, it may never take that many amount of time. So thus we are saying that f of n is equal to O of g of n. Now, similar to this big O notation, we have theta notation and omega notation. So theta notation is for average case and omega notation is for, sorry, omega notation is for, sorry. Theta notation is for average case and notation is for best case. Now if I see this image graphically, what is there in the image? We have x-axis and y-axis. The big O notation's upper bound. As I told you, big O notation is trying to give us the upper bound. Now this upper bound, if I say it in terms of the graph, it is represented like this. Nothing but I have a particular g of n. Okay, so those will be somewhat going up and down here whenever the f of n's value is least value. As it goes upwards, it is linearly going with the what? G of n. Okay, so that is last, that is the upper bound. This g of n would be the upper bound for f of n equal to 2n plus 3. The idea of using the big O notation is to give an upper bound of a particular function. Okay, as I told you, it is always giving you the upper bound, which is nothing but which says for the worst case time complexity. Okay, means in at worst time, how much time it will take, not the best time. Means best time means a minimum number of time what it will take in order to run. Okay, we will be always considering after entire operation is done, how many number of time it will take. So it provides an assurance that a particular function does not behave suddenly as a quadratic or a cubic fashion. It just behaves in a linear manner in a worst case. Okay, yeah, means what the thing here it says is, once we found the upper bound, it says that now this is going linear to this, right? So this is in the straight line, this is in the straight line. So they are linear to each other. Okay. Now it may suddenly it may, when I come here, suddenly it may go come here and then it goes like this. So non-linear behavior or cubic behavior, it may won't show. It will only show the linear behavior because we have set a upper bound, and that upper bound is in such a way that it is working with the linear way. Okay. So that is the graphical representation. Remember, f of n will always give us the upper, sorry, big O notation will always give us the upper bounder, okay, which is nothing but my g of n with respect to f of n, whatever function I have. Next notation is the omega notation. Okay, so the symbol there is a Greek letter, which is omega. Now we see similar to that, here also the substitution for equation is there wherein we are proving the equation. Yeah, so we'll see now omega notation. It basically describes the best case scenario, which is opposite to the big O notation. As I told you, big O notation will always check for the worst case notation. Okay, it will be always for the worst case. But what is omega notation doing? It is always looking for the best case. Okay, so that is why one is worst and one is best. That is why it is a ditto opposite of which one? Big O notation. Okay, omega notation is a Omega notation is the this one, what opposite of big O notation. So now it is a formal way to represent the lower bound of algorithm's running time. So if I say big O notation is the opposite of omega notation, and if big O notation is considering the upper bound, then it would be our omega notation would be considering the lower bound, correct? Yeah. So what it does is it measures the best amount of time an algorithm can possibly take to complete, or the best case time complexity. Okay, why we need omega notation? In order to measure the amount of time, the best amount of time taken by the algorithm, not the worst amount. Okay, not the most amount, but the least amount an algorithm will take in order to complete its execution is measured by the omega notation. So we also call it as best case scenario also, or else we call it as best case time complexity. So it determines what is the fastest time that an algorithm can run. Okay. And if we require that an algorithm takes at least certain amount of time without using an upper bound, we use big omega notation, that is the Greek letter omega. Okay. So what is it? If we require that an algorithm takes at least a certain amount of time without using an upper bound, got it? So upper bound means it is giving us the worst case. So without using the upper bound, if we actually want an algorithm which is taking the least amount of time, so for that you have to depict or you have to show the big omega notation. So whenever you see this symbol, whenever you see this symbol in the terms of complexity, then what it would be, in the term of complexity, whenever you see the symbol, it would be which one? It would be either overflow. Okay, so when your system gets overflow, it will give you that. That is either, I'm telling, I'm not saying it will give that. And one more thing is or is there. So that is why we have to consider this one also, that one also. Okay. And now so we have omega notation and okay. So now it is used to bound the growth of the running time for the large input size, correct? This is as similar to big O notation. Okay. Yeah, so that is about the big O notation. We will see some of its equations for this. So we are having the same equation, whatever we have seen earlier, like if two functions are there, which is f of n and which is g of n, and they are defined for the positive integers, then f of n is equal to omega of g of n. Here, one thing, students, mainly you listen carefully to this one. Like whenever you have, okay, so whenever you have, what you have, um, is two functions. Okay. Yeah. So whenever I have two functions f of n and g of n, now this, if I see, it is similar to our this one. Earlier we have solved, right? Big O notation. It is same, but instead the symbol what we are writing was omega O, right? Because it was big O notation and this is big omega notation. So this we need to consider whenever we are going to particularly say about worst case, best case, and um, average case. Okay. Yeah. So if there exists a positive constancy and not such that, now tell me when we actually want to take the photo of the stadium and post it somewhere else saying that I have done the homework or something like that, what will happen? You will notice it, correct? Okay. Yeah. So okay. So if here if I have two functions f of n and g of n in the which one? big O notation will be using O, and here I'll be using omega. Okay, now whenever I want to say that I want to know the worst case, I'll be making use of O notation. And whenever I say I want to make use of, or I want to learn the complexity in terms of worst case, and in case of worst case scenario, we would be using this omega. So now if I have two functions which is similar to big O notation, f of n and g of n, and the condition for the earlier one, which is a big O notation, was what? It was your f of n needs to be less than the c into g of n. But here the condition is completely opposite, because we have seen that this is completely opposite compared to the O notation, correct? Compared to the O notation, omega notation is completely opposite, okay, which is opposite to big O notation. And what was the equation? What was the condition? F of n is less than or equal to g of n, okay? And then for the c should be non-zero, and also, sorry, c is a constant and n should be non-zero. All the input must be present. I mean, input in the sense the number of event participants needs to be there. And then uh, okay, then we have the equation, okay? So f of n greater than or equal to c into g of n. Earlier in the big O notation, we had f of n is less than or equal to c into g of n. Now we have f of n is greater than or equal to c of, or sorry, c into g of n, which is nothing but here we are considering for the best case scenario. So g of n represents the lower bound function, and yeah, since it is best case, I'll be considering the lower bound function, and c is the best constant that ensures that condition holds. Okay, yeah, and then after that is n naught is the threshold beyond which the condition is always true. Okay, so n naught becomes always true. So there is one example, simple example to similar to this one, which one we have seen there for big O notation, right? In the similarly, we have the equation for big, what's your name? Okay, so big, okay, big O notation, correct? Yeah. So f of n is equal to 2n plus 3 and g of n is equal to n, and f of n is equal to, here what is the notation? Omega notation. Okay, big omega of g of n. So what is the meaning? What I have to do, instead of f of n, I'll be substituting g 2n plus 3, and instead of g of n, I'll be substituting n, and I'll be multiplying it with the constant. After that, what is the step one? We'll be choosing some constant. So here, even if I choose the constant 1, what will happen is 2 into 1 plus 3 is how much? 2 into 1 is 2, 2 plus 3 is 5. 5 will be obviously greater than or equal to 1, correct? So here also the bound will be matching. Now, here it is checking for n naught. Now, first thing is we are checking for the value of c. When the value of c is 1, even the value of c is 1 also, there we don't have to much think about it. Correct? We don't have to much think about it. So it will be satisfying the condition, even if the C value is 1. Now we'll check what happens if the number of input value is 1 and 2. So obviously it is going to um, accept it. Okay, I mean accept the fact. So clearly for all the values of n greater than or equal to 1, the condition holds. So now here this, in order for this condition to be true, the n shouldn't be 0. If n is 0, your entire thing is going to be 0. And always we know that the inputs are very much important whenever we train the model. Okay. So we have some explanation of omega notation here. This is very simple. So as I've told you, it is best case, correct? So in best case, my g of n would be always in the lower bound. Okay, and we say that below this line, the f of n will never come because my omega notation will always depict the worst case scenario. So as we can see in the figure, g of n function is the lower bound of f of n function when the value of c is equal to 1, and therefore this notation gives the fastest running time. And then but we cannot move in yes, but we cannot move. We are not more interested in finding the fasting running time, correct? Yeah, so as we can see in the figure, g of n is a lower bound and therefore this notation gives the fastest running time. Then we are not more interested in finding the fastest running time. We are interested in calculating worst case scenarios because we want to check our algorithm for larger input, what is the worst time that it will take so that we can take further decision in the further process. So that is how everything will be integrated together. We'll be having best notation, worst notation, and one more is, sorry, best case, worst case, and one more is average case. Okay, depending upon that, we'll be having notation like big O notation, omega notation, and theta notation. So this is the diagram for it, and the theta notation we'll be discussing in the next class. Okay, yeah. So that is mainly for the average case scenarios. So today we have seen about the big O notation and how the calculation of features in the inside will be happening. So all the things, whatever we want for is done by the programming. So we are importing just the functions from different libraries of Python, and then we are going to implement the code. So that is very easy. So that's all for today. Thank you.